Welcome to another edition of The Explainer. I am seriously thrilled you're here. Today, we're going to crack open a truly fascinating algorithmic puzzle, one that basically bridges the gap between a standard spell checker and a pretty powerful search engine. We're talking about designing a data structure to insert and search for words, but with a major, mind-bending twist, the inclusion of wildcards.
Picture this. You're playing Scrabble, or maybe you're stuck on a crossword puzzle, and you've got a word right on the tip of your tongue. You know for a fact it starts with R and A, but the last letter? It's a complete blank. So how do you search a dictionary when you simply don't know all the letters? Well, that's the core mystery we are unraveling today. We need a system that can not only store a massive list of words, but can gracefully and quickly handle searches when we're missing information.
Here's our roadmap for today's explainer. First, the wildcard problem. Second, building with a trie. Third, the wildcard twist. Fourth, recursion to the rescue. And finally, measuring time and space.
All right, let's jump into part one, the wildcard problem.
Okay, let's establish exactly what we're trying to build here and what constraints we're operating under. First off, our data structure will only deal with lowercase English letters. Nothing too crazy there, right? But the second point is where the real magic happens. A search word can contain a dot character, and this dot acts as a wildcard, representing literally any single lowercase letter. Let's look at a quick example. If we insert the words band, rat, and ran into our system and then search for r.a, the system should return true. Why? Well, because that dot can act as a T to make rat, or an N to make ran. Both are in there. However, if we search for b ... looking for any three-letter word starting with B, the system absolutely must return false. Sure, we have band in the mix, which starts with B, but that's 4 letters, not 3. So the big question is, how do we actually store these words to make searching efficient?
Moving on to part two, building with a trie.
The absolute best tool for this job? It's called a trie. A trie, which is often called a prefix tree, is this incredibly useful tree-like data structure specifically designed to facilitate the rapid insertion and search of words based on their prefixes. And honestly, the beautiful thing about this specific problem is that inserting a word into our structure is completely identical to a standard traditional trie implementation. The wildcards? They only complicate the search function.
Okay, let's dive into this and actually visualize it. Here's a standard trie populated with our earlier example words, band, rat, and ran. We start right at the top, at the empty root node. Notice how the words share paths if they happen to share a prefix. Rat and ran both start with R and A, so they share those first two nodes before finally branching off into T and N. But the absolute most critical part of this diagram? It's those little dotted lines pointing to is word equals true. You see, a node doesn't just hold a letter. It holds a flag indicating whether that specific node marks the end of a valid inserted word. Like if you trace down to B, A, N, that sequence definitely exists in the tree as part of band. But there is no is word equals true flag on that N because we never inserted the word ban all by itself.
Which brings us to part 3, the wildcard twist.
Now let's break down the fork-in-the-road logic our algorithm has to process at literally every single step of a search. When traversing down the trie, we essentially run into 2 distinct scenarios. Scenario 1, we encounter a standard letter. This one's easy. We just proceed down the specific child node that matches that letter, exactly like a normal trie search. Scenario 2, though, we encounter a wildcard dot. Here we can't just pick one path. Because the dot could be anything, we must explore all existing child nodes from our current position. We essentially clone our search effort, pushing forward down every single possible branch to look for the remainder of the word.
Let's actually see this in practice. Say we're searching for R dot. The first character is R, a standard letter, so we follow the route to the R node. The second character is A, another standard letter. We follow the R node straight down to A. But now our third character is the wildcard dot. We're currently sitting at the A node, and we have to look at its children. The A node has 2 children, T and N. Because our search character is a wildcard, it happily accepts both. And crucially, both the T node and the N node have their is word flag set to true. Boom, the search is a success. We found a valid path. In fact, we found 2. But what happens when the wildcard isn't conveniently placed at the very end of the word?
And that leads perfectly into part 4, recursion to the rescue.
And this brilliantly illustrates the true power of recursion in our algorithm. Let's say we're now searching for .an. The wildcard is the very first character. This means right from the root we don't know which way to go. So what do? We check them all.
We recursively call our search function on every child of the root, looking for the remainder of our string, which is n. Let's check out the left branch first, the b node. We treat the dot as a b and continue searching for n. We go to a, then we go to n. We successfully traced out ban. But look closely at that n node on the left. It's colored yellow, and its isWord flag is false. The word ban was inserted, sure, but ban was not. So this entire left branch fails. But remember, our recursive search also traveled down the right branch. It treated the wildcard dot as an r and then searched for an. It traverses down to a, then n, and this time the n node on the right has isWord equals true. The right branch is a massive success.
This is the essence of why recursion works so elegantly here. I absolutely love this quote from the source material. As soon as we find one branch that represents a word matching the search term, we return true. Think of it like a team of scouts. The moment they hit a wildcard, they split up and explore every possible cave and tunnel. If a scout hits a dead end or a node that isn't a complete word, they just quietly fail. But the very moment just one single scout finds the target, they signal the whole team, and the overall search returns true. We don't need all paths to be valid. We literally just need one.
Finally, Part 5, Measuring Time and Space.
Okay, so we've built this highly flexible search function, but what does it actually cost us computationally? Let's contrast a standard trie search with our new wildcard search. In these formulas, keep in mind that k represents the length of the word. For a standard search, the time complexity is incredibly lightweight, big O of k. You just step down the tree, character by character. The space complexity, big O of 1. Basically nothing, because you were just moving a pointer down the tree. But look at the wildcard search. The time complexity completely skyrockets, and the space complexity jumps to big O of k, simply because of the memory required to maintain that recursive call stack.
So the crucial point here is this massive number, big O of 26 to the power of k. Why is it so explosive? Well, this represents the absolute worst-case scenario, where the search word consists entirely of wildcards. Just imagine searching for a 10-letter word where every single character is a dot. For the first dot, you check all 26 possible alphabet letters at the root. For each of those 26 letters, the next dot forces you to check 26 more children. 26 times 26 times 26. It grows exponentially. While our algorithm is undeniably brilliant, a search heavily populated with wildcards forces the computer to do just a colossal amount of recursive branching.
Just to round out our analysis, let's briefly review the insertion complexity. Thankfully, adding wildcards to our search didn't ruin our insert function at all. The time complexity to insert remains completely standard at big O of k, because we only ever have to traverse or add at most k nodes for a word of length k. The space complexity is also big O of k. This represents the worst-case scenario where the new word shares absolutely zero prefixes with any existing word in the trie, meaning we have to allocate memory for k entirely new nodes.
So we've seen how adding just one simple dot can completely transform a straightforward dictionary lookup into a massive, multi-threaded recursive mission. It empowers our search to be incredibly flexible, but as we saw with that 26 to the power of k worst-case scenario, it introduces a massive computational vulnerability. Which leaves us with a critical engineering question. Is the hidden cost of ultimate search flexibility always worth the potential for explosive time complexity? When building real-world systems, how much flexibility are you actually willing to sacrifice for guaranteed speed? Think about that next time you use a search bar. Thanks for joining me on this explainer, and keep learning.